Hello, my AB Calc kids. We are looking at section 4.2 today on position, velocity, and acceleration. And this is probably one of the more important sections that we cover. Lots and lots and lots of questions on the AP exam deal with position and velocity and acceleration. So this one's a biggie. Here we go. Mr. Bruce is playing catch with his best friend himself. He throws a tennis ball straight up into the air. The height of the ball is modeled by S of t. They use S of t many times as a position function. So that's the abbreviations they give it, S of t. Sometimes you'll see X of t, but the popular one is S of t. And they give you negative 4.9 t squared plus 18t plus 2, where t is time in seconds, and S is the height of the ball from the ground in meters. So if I were to graph that, here's my height, right? Here I am. Or here's Mr. Bruce playing catch with himself. He throws the ball up in the air. It goes to its highest place, comes down, and hits the ground. Now, my first question for you is, if I look at this one, the parabola, the upside down unhappy parabola, does not start at 0 like we oftentimes would see. So how come it starts up here at, like, I don't know, 2.5, 3 feet? And we discussed this in class, and you said to me, well, that's because he's holding the ball. The ball isn't on the ground, the ball is in his hand, and since it's in his hand, it's off the ground by, I don't know, 2.5, 3 feet. All right, so he throws it up in the air, throws the ball up in the air. It gets to its highest location, and then it comes down here, and it does actually hit 0 because it hits the ground. So over here on the left, these values are my height in meters, and across the bottom is my time in seconds. And I just graphed for you what that ball looks like, where the ball is at each time period between 0 and 4 seconds, whatever it is. Okay. If I asked you then for the velocity of this, well, the velocity would be, and you do have an equation. If I think about it, actually, let me put it down here. This was my equation for this guy. He was y, or I should use S of t, right? S of t equals negative 4.9 t squared plus 18t plus 2. Well, if I look for the velocity is the derivative of position. And they use v of t to represent velocity. So let's think about what that equation is, and then we'll talk about the graph. If I take the derivative of this, you're like, that's easy peasy lemon squeezy. Take 2 times negative 4.9, I get negative 9.8 t plus 18. Now, some of you that take physics or have had physics, you can see that these equations kind of line up with things you learned in physics, right? With gravity and the pull of gravity and those types of equations that you use. So all these things kind of link together with what you've learned already in physics. So if I asked you to graph me this line, you would say, okay, I've got a y-intercept that's 18. Well, here it is. And I have a slope that's negative 9.8 or like negative 10. So that's kind of where I'm going with this. Notice this coordinate right here. He's kind of cool. Right, so if I graph the line, here I am, got my y-intercept, got my slope, it looks like this. But this, where it crosses the x-axis, where is that place? Maybe it's at like maybe 1.8 or something like that. So I'm going to say it's at, we're just going to estimate it to be 1.8 comma 0. What's the significance of that if I look at this first graph? And if I look at this first graph, can you see that here at 1.8, where x is 1.8, that's where I have the highest point, the maximum of my position function? What's the slope of the tangent line there? The slope of the tangent line would be 0. Oh, wait a minute. The slope of the tangent line 0, well, that's what this is saying. It crosses through the x-axis. That's where my slope is 0. So this represents, my velocity represents the slopes of the tangent lines at these different places. But this is really significant right here. That's the point 1.8, maybe 18. That x value that you've got there is where you're going to have your slope being 0 which is where it's going to cross through the axis here, the x-axis. So all these things kind of link together, and that's what this section's really all about. All right, if I go sloping one more time, if I look at this guy, the slope of this line is negative 9.8. If I find the acceleration is the derivative of velocity. Well, the derivative of velocity is negative 9.8. And you can see that that's going to be, if I were to graph this, y equals negative 9.8, it's going to be a horizontal line, and that horizontal line is going to be at negative 9.8. If I think about units, now you saw this in the last section. If I'm in velocity, I'm in meters per second in this case. If I take one more derivative, now I'm meters per second squared. So you can see all of that, meters per second squared. So putting this all together, position is s of t. Sometimes they use x of t. You're going to see it in a few minutes. Velocity is the derivative of position. Acceleration is the derivative of velocity, but that would be then the second derivative of position. So if they want to find acceleration and they give you the original function, the position function, you've got to go twice. Two derivatives to get there. Change of position, if the velocity is negative, less than 0, it means the particle is moving left if it's moving along the x-axis, or down if it's moving along the y-axis. They'll tell you whether it's moving horizontally or vertically. If I have a velocity that's greater than 0, then the particle is moving right if it's along the x-axis, or up if it's along the y-axis. Kind of makes sense, right? And if it's 0, then the particle's not moving, it's at rest. So when they ask you, is the particle moving left, is the particle moving right, all of those things is all based off of the velocity, the first derivative. So maybe we want to say that over here, the first derivative. It's all based off the first derivative, if it's moving right or left, or up or down. If they ask you for the average velocity, well, we learned this way back when. Average velocity just means the same thing as slope. And slope would be, let me fix my brackety thing. Here we go. Average velocity is like slope. So s of b minus s of a over b minus a, because remember it's an s. I think we usually used f of b minus f of a over b minus a. Same thing, but this is a position formula. But they have to give you a starting and stopping place. They have to give you an interval to be able to do that. So average velocity is the same thing as the slope. This is the old slope formula, nothing new. And the last piece is speed. Speed is the absolute value of velocity. Then the last, the really last piece is they're going to ask you, is the particle moving, is it speeding up or slowing down? Sometimes they'll ask you that question. And if they do, what you need to do is check the velocity and check the acceleration. If they have the same signs, in other words, if they're both positive or both negative, then it's speeding up. If the velocity and acceleration have different signs, then it's slowing down. So they give you a chart here and they say, okay, well, are these situations where it's speeding up or slowing down? I don't care about the t-values. I'm comparing the velocity and the acceleration. They're different signs. Positive 3, negative 4, slowing down. Negative 2, positive 7, slowing down. Positive 1, positive 0.1, same sign, speeding up. Negative 1, negative 1, speeding up because of the same signs. Displacement is the net change in position. So you're taking your s of b minus s of a. Kind of like just your numerator up here of your slope. This is talking about how far have you gone. Displacement, how far have you gone? So if I have walked for 15 minutes, then wherever I stopped at the end of the 15 minutes, I'm going to take that place and subtract away where I started from. So that's my displacement. How far have I gone? Net change in position. So s of b minus s of a. And I'm taking you through where we ended up in class, and then I'll pick up from there with writing down some note things. All right, so here comes the next piece. Let's see. Again, this was where we were in class. So the position is the x-coordinate of the particle moving along the x-axis. In other words, it's moving left and right. is modeled by this function. X of t they use instead of using S of t. So X of t, where X can be measured in centimeters and t is in minutes. If they give you units, you want to make sure you include units in your answer. So find the displacement of the particle during the first 2 minutes. Well, the first 2 minutes go from 0 to 2 minutes, 0 to 2. And remember on the page we just talked about, my displacement was S of B minus S of A. Well, this is an X. All right, so that's a fine. X of 2 minus X of 0. So you plug a 2 into your position formula. You plug a 0 into your position formula. And then you calculate it out. So this becomes a -5. This becomes a -3, minus a 3, minus 3. And -5 minus 3 is a -8. Displacement is how far you've gone. So you've gone 8 centimeters in negative. That means it's gone left, ultimately left for this thing because it's a negative. So -8 centimeters is where you're at. Find the average velocity. Well, average velocity for these guys is going to be, remember, like the slope formula. So X of 2 minus X of 0 over 2 minus 0. You just figured out what X of 2 minus X of 0 is back in this first one, in number 1. So that whole thing's -8 divided by 2 gives me -4, but now on velocity, I'm like a first derivative. So I am centimeters per minute. Then they want you to find the actual velocity. Notice they didn't use the word average anymore when the time is 4. Well, that makes me go back to the original function and find the derivative. So I want to figure out the velocity formula, go back to the original, take the derivative, 3t squared minus 8t. That's this. Plug a 4 in. Okay, plug a 4 in. Calculate it out, you get 16. It's velocity, so it's centimeters per minute. And then number 4, they say, okay, we'll find the acceleration of the particle when t is 4. So I'm going one more derivative. 3t squared minus 8t becomes a 6t minus 8 when I take its derivative. Plug a 4 in. Gives you 16 centimeters per minute squared. Watch your units. Now you're one more derivative. So that denominator ends up being squared. And then the last piece that we were able to get to is the particle speeding up or slowing down at t equals 4? Well, I have to compare the velocity with the acceleration and see if they have the same signs or different signs. This is a positive 16. This is a positive 16. They've got the same signs. And so therefore it's speeding up because they asked you to justify it. A of t, I guess I should say A of 4. Right? They were very specific. What's it doing at 4? A of 4 and V of 4 have the same signs. And that was where we stopped in class. So we're going to continue on, and I will do some of the examples as well, some of the practice problems. But here's the next one. The hardest part about this particular section is how you answer the problem depends on what they give you. I'll say it again. How you answer the problem depends on what they give you. In that last set of problems that we just did, 1 through 5, they gave you the original position function. But look at this one. This time they give you a graph. They don't even give you a number function. And they say that this is the graph of the velocity. In other words, you're looking at the first derivative. This is not the graph of the function. This is the graph of the first derivative. And so the things you're looking at when you're answering these questions are going to be different than if they had given you what the picture of the original function was. So your answers are all based off of this velocity being the first derivative. You know what, I want to do this on a different piece of paper. Hold on a second. These are our class notes, so I'll do that again here. I want to save that for when we're in class together so I can continue on with that one. All right, first derivative. So let's think about this. This is the velocity graph. When is the particle moving right? Now, if you remember back on the front page, This whole section right here is going to help us answer these first few questions. So they want to know, when is the particle moving right? Well, the particle's moving right when the velocity is positive, greater than 0. All right, so let's write ourselves a note about that. When is the particle moving right? And the particle is moving right when the velocity is greater than 0. And we get that from the front page there. Let's go on to answer the next piece here. Might as well answer this guy here. When is the particle moving left? And then we'll look at the graph and answer the actual question. Left when the velocity is less than 0, right? That's what we said from that front page. So let's try this. Velocity is greater than 0. This is the velocity graph. If it's greater than 0, that means it's above the x-axis. Maybe I'm going to change my color and give you a clue in here. Above the x-axis. Right, because that's where your v of t values are going to be greater than 0. Well, where does that happen? So if I look at this, oh, it's above the x-axis between 0 and 1. 0 to 1. Then it goes below the x-axis for all of this. And then it goes above the x-axis again. We're going to estimate about where this coordinate is, because see how it doesn't go through perfectly? I'm going to just say 4.7. So from 4.7 to 7, where the graph stops. That's when it's above the x-axis. You see that? Well, the velocity is negative when it's below the x-axis. Oh, rocket science there, right? So look at the graph. Where is it below the x-axis? Well, that would be between 1 and 4.7. And see how they asked you to justify? You absolutely, this is the justification right over here, the part that I have in blue. You can include this, but really what they're looking for as a justification is this part over here. Okay? When is the acceleration positive, negative, or 0? Well, how on earth am I supposed to get acceleration out of a velocity graph? Like, I have no idea, right? Well, if acceleration is the derivative of velocity, then what I'm looking for is what the slopes are. So it is positive acceleration, because they didn't actually ask for justification, but it's going to be easier for us to answer. Positive acceleration when it's a positive, when v of t has a positive slope. All right, well, let's continue on with that thought before we answer the question. It's going to be a negative, they didn't give me much space here, acceleration when v of t has a negative slope. And it's going to be a 0 acceleration when v of t has 0 slope. The slope is 0. All right, let's go to the graph and check out the slopes. So the first thing, if I start reading this from left to right, the first thing I've got is going from 0 to 2. And you can see the slope of that is a negative slope because it's a negative line. So negative slopes go with negative acceleration. That would be over here from 0 to 2. Do we like red? I don't know. I started in red. There it is. Then I keep reading the graph. From 2 until I get to 6, this whole section, this whole line is all positive. Positive slopes mean positive acceleration, so that means from 2 to 6 over here. And then I look at the next piece from 6 to 7. That's a negative slope again. So over here with negative slope is going to be a negative acceleration from 6 to 7. And does it ever have a zero acceleration? We say nope, never. When does the particle have the greatest speed? Well, speed, if you remember, is the absolute value of velocity. So really what you're looking for this guy is when your, I'm going to say your y value is farthest from the x-axis. You're looking for the point that's farthest away from the x-axis. So this guy's pretty far away, right? At t equals 0. He's a distance of 2 away. Remember, it's the absolute value, but this is a positive 2. If I look over here, he's pretty far away from the x-axis. He's a value at negative 2, but when I take the absolute value of a negative 2, I get positive 2. These guys are not as far away. This guy's only 1 away. So the guys that are biggest or farthest away from the x-axis are these two places. So when does that happen? So that happens when t equals 0 and when t equals 2. It didn't ask you what the actual y value is. It's just saying when does that happen? When is a t value? When is a time? They did not give us units on this, so we did not have to include units in our answers. When is it speeding up and when is it slowing down? Well, that goes with comparing your acceleration and your velocity. So speeding up is when a of t and v of t have same signs. There's your justification. And then slowing down would be when, so you can see it, when a of t and v of t have different signs. Now remember, you're looking at this velocity graph, and then you're comparing it with what the slope, the acceleration, is doing there. So the first part of the graph that I look at is here, from 0 to 1. Well, that has a positive velocity because it's above the x-axis, but it has a negative slope. The slope of that line is negative. That would be where it's slowing down. So might as well put that in my slowing down thing here. First place that it slows down is from 0 to 1. The next section of the graph goes from 1 to 2. Well, 1 to 2 has negative velocity values. It's below the x-axis. And it has a negative slope there. So they have the same signs. They're both negative. So between 1 and 2, that's here. Then I'm going to the next set. The next set goes between 2 and 4.7. Well, from 2 to 4.7, I have a negative velocity below the x-axis, but a positive slope. Negative, positive, different signs. Here it is. So from, different signs. Negative, positive, different signs down here. 2 to 4.7. And then from 4.7 to 6, they're above the x-axis, positive velocity, positive slope, that's same signs. So from 4.7 to 6, and then the last piece goes from 6 to 7, positive velocity, negative slope is different signs. So 6 to 7 goes with that guy. All right, again, what they give you, how you answer the question is going to be different depending on what you're given originally. This one we were given a velocity, so we were looking at different types of things. All right, let's try some practice problems. I'm looking at what we might want to do here. Let's try number 3. Number 3. Actually, I'm going to change my mind. Let's do number 2. Because number 2 has, I think I differ from what they think about on the from the curriculum perspective, from the answer key. I think I might have something a little different, but let's see. Number 2, a ball is dropped off of a 1,200-foot cliff. The height of the ball over time is modeled by this function. In other words, that's your position function, where h is the height of the ball and t is the time in seconds. Find h prime of 3 and explain what it means. Find h double prime of 3 and explain what it means. This is just like they're linking this with section 4.1. Remember when you had to explain your derivatives and what they meant and such. So this time they give us an equation. I love it when they do that. H prime of t, they want to know. Well, with an equation, that's pretty easy. You just find the derivative. Well, 1200 is 0. Negative 16t squared is negative 32t. Do you notice that with physics? They want to know what is h prime of 3. Well, h prime of 3, plug a 3 in. Negative 32 times 3 gives me negative 96. Now, negative 96 what? What are the units for this? So let's see. H is the height of the ball, and t is the time in seconds. Did they say what the units were for that? They didn't, but I think they meant feet. Let's go with feet. So what does it mean? It means at 3 represents your seconds. At 3 seconds, the ball. Now, is the ball getting higher, like increasing in height or decreasing in height? And we know it's decreasing in height because of the negative here. So it's falling, decreasing in height, falling. Here's your words, right? At a rate of 96 feet per minute. Oh, seconds. My bad, seconds is it. Feet per seconds. They did give you the unit for that. Now they want you to find the second derivative at 3. All right, well, here's your derivative formula, right? So if I find the derivative of that, my h double prime, that's going to be negative 32, and that's it. Now think of, I guess I should have put this over here. This was feet per second also. This one's going to be feet per second squared, right? This was now the derivative of the derivative. And so now you're at a second derivative, so you've got feet per second squared. The other thing, remember, if I am a second derivative, I have to use that word rate twice, just like we did back in section 4.1. So when I have to explain for this one, which by the way, h double prime at 3, there's no t for me to put this into, so my answer stays the same. It's still negative 32 feet per second squared. That didn't change. So let's see if we can put a meaning to this. At 3 seconds. The rate of the falling ball is, now here's where it gets a little dicey. It's actually, and I'm going to write it and then I'm going to talk about it. The rate of the falling ball is increasing at a rate of 32 feet per second squared. Here's where it's dicey. See how you have a negative value here? Your acceleration is negative. Shouldn't I be using the word decreasing over here? And this is more of a lesson in logic, if you think about it, because you've already used the negative here, the falling ball. So if I'm thinking about this, at 3 seconds, the rate of the falling ball, the ball's already going down, it's getting faster, because remember, the value of this is increasing at a rate of 32 feet per second squared. I don't love the wording of this one. I think it's rather confusing, and we can debate more about it in class, but that's what the curriculum people are saying. And again, we'll debate about that when I see it together. So really, this word is what I'm unhappy with. I'm not 100% comfortable with that, the way that that's worded. But it is what it is. All right, let's try number 4. Number 4, all of this depends on what function you're given. So if I'm looking at number 4, I got to figure this out. This is really super duper important. The particle moves on the number line. The graph of s, which is f of t, shows the position. This time I'm looking at position. So I am not looking at velocity. This does not represent the velocity. This now represents the position. What we're going to be looking for is going to be different than when they gave us that velocity graph. So I've got to kind of really watch what I'm doing here. So when is p moving left? Well, if I'm looking at the position graph, then all of these lefts and rights are based off of the first derivative, my velocity, but I don't have a formula for me to be able to figure out what the actual velocity is. So what I have to then do is revert to slope. What's the slope doing? So it's going to be moving left when the slope is negative, and it's going to be moving right when the slope is positive. Because that's what's going to equate to my velocity. All right, so let's see. Moving left. If I take this graph and just take each piece, oh, by the way, it's at rest when it's constant, when the slope is 0. Oh, I should put it this way. Hold on. If I keep it consistent with how I wrote it, it's at rest when the slope is 0. So let's read the graph one piece at a time. First piece. This first section is a positive slope from 0 to 1. Positive slope is right. 0 to 1. From 1 to 2, it's constant. It's 0. Remember Slope Dude? The Slope Dude thing? This is 0 fun. All right, I'm going from 1 to 2. If I go to the next set, the next piece of this graph goes from 2 to 3. That whole section is a negative slope. So that would be left, 2 to 3. Then it's constant again from 3 to 5. And then it's a negative slope from 5 to 6. Negative is up here, 5 to 6. And there you go. You've just determined when it's moving right, left, or at rest. Then it says, okay, well, graph the particle's velocity. Huh? How am I supposed to do that? Well, if the velocity is the slope, then I guess I need to figure out what the slopes are in these sections. So if I look at the first section of the graph, this first piece, from 0 to 1, I'm going to do it over here, from 0 to 1, if I look at that section, what's the slope of that piece? Rise over run, 2 over 1, gives me a slope of 2. Then I'm going to go to the next piece, and then I'll graph it on there in a minute. I'll show you how the graph works. My next piece goes from 1 to 2. 1 to 2 is my section. My slope is 0. My next section goes from 2 to 3. And if I look at its slope, rise over run, ooh, this one is 4 over negative 4 and then left 1. So this one's a negative 4. Next piece, easy peasy, 3 to 5, has a slope of 0. And the last piece goes from 5 to 6, and that has a slope of -2. Totally just reading the rise over the run. All right, I'm going to go with my highlighter, and I'm going to put this on here. So between 1 and 2, I have a slope of 2. All I need to do is put a little horizontal line there at 2. Between 1 and 2, I have a slope of 0. Well, 0 is down here on the x-axis. Between 2 and 3, I have a slope of -4. That's way down here. My slope's -4. Between 3 and 5, I have a slope of 0, back on the x-axis. And between 5 and 6, I have a slope of -2. That would be right here. There are a bunch of just little horizontal lines that tell you what the slope is in that particular area. That would be what your velocity function would look like. They are not connected. You'll notice that. They're not connected, yeah. You're just going from one slope to another slope. All right, there's number 4. Let's try number 7 next. We're getting close to done, kiddies. Number 7. I'm just trying to pick the ones that are a little different. So now they give us a table. So you see that's different than some of them where they give us an equation, some of them they give us a graph. This one's now a table. So how do you deal with tables? Well, kind of the same way. You're looking at this table and trying to figure out what's it a table of. Is it a table of your position function, or is it a table of your velocities or accelerations or whatever? You can see that this guy's all about velocity. So they're giving you the first derivative. They're giving you the velocity. The data in the table gives selected values for the velocity in meters per minute of a particle moving along the x-axis. The velocity is a differentiable function. So remember, if it's differentiable, it's got to be continuous. Okay? That's kind of what they're saying that. So this has to be a continuous function. At t equals 0, is the particle moving to the right or to the left? Well, remember, it's based off of the velocity. So you're looking at, is it positive or is it negative? They give you the velocity values. So at t equals 0, I get -3. So if it's a -3, I know it's moving left because the velocity is less than 0, is negative. Question is it moving left or right? We said left, gave it a justification. There you go. For B, is there a time during the interval from 0 to 12, that's the chart encompasses, when the particle's at rest? So think about this logically. If I were to plot these points and connect them, because it's a continuous graph, this would be 0, -3. This would be 2, 2. If I just do a quick plot of that. 0, -3. 2, 2. It's a continuous graph. This is my velocity. Is there velocity? If it's at rest, then I know my v of t has to equal 0. Is there a place there where it has to be 0? And you can see it crosses the x-axis. So yeah, there's got to be a place right here where it crosses the x-axis where you have a velocity that's 0. The rest of the plotted points don't really matter because they all stay in positive territory. They're all going to be up above that x-axis. So it's just this guy here going from a negative to a positive. You know for sure there's got to be a time in there where it's at rest. And so we say yes, between 0 and 2, because the velocity, v of t, changes from negative to positive. And remember this? By the intermediate value theorem, which says it has to connect those points as continuous function, must be 0 between 0 and 2. I probably could have written this better, but you get the idea. All right. Then it says use the use the data from the table to approximate v prime of 10. In other words, they want you to make a derivative out of this. So think about this. If I've got a table of values and you want to find the derivative, how do you do that? At 10 nonetheless, 10 that isn't even on your chart. So if I want to figure out what it is at 10, I have the only thing I can do is figure out what the slope is. That'll give me a derivative. That's my only hope from a chart. So I'm going to go a little to the right and a little to the left of 10. So I want to know what v of 12 is minus v of 8 over 12 minus 8. Because they're the values I have that are close to 10. So I go to the chart, 5 minus 7, 12 minus 8 is 4. I get negative 2 over 4, and that gives me a value of negative 1/2. I guess I could put units to that, right? These are in meters per minute, so this is now taking the derivative of that. This would be in meters per minute squared. All right, explain the meaning. Here we go again. Of v prime of 10, what you just found over here, we know that 10 represents the minutes, so at 10 minutes, the particle's velocity it's negative, decreasing, at a rate of 0.5, 1/2 meters per minute squared. All right, that's where we're going to stop. I think you have the knowledge now to be able to answer the rest of the questions. There are numbers 1 through 9, but obviously they've got lots of parts, A, B, C, D kind of stuff. If you have questions or troubles, shoot me an email. Otherwise, happy section 4.2. And we'll move on to 4.3 next. Have a good one.